Hi, my name is Megan Stasik, and today I'll be presenting Where's My Copper, which discusses the functions of EPR, electron paramagnetic resonance spectroscopy. So the goals for today are to go over background information and theory, hypotheses, experimental methods, data and results, additional discussion points, as well as larger applications. So EPR is also referenced as ESR, and this is a technique that is useful for determining the structure of complexes containing unpaired electrons and may be used to detect transition metal ions and free radicals. So in this experiment, the ESR spectra of these three histidine copper coordination compounds will be analyzed to confirm ligand arrangement. So histidines are strong metal ion coordinators in proteins and are essential amino acids that contain an imidazole side chain. The imidazole components contain two nitrogens that are able to bind to copper. Now, before we jump into the hypotheses, let's start with the basics. Electrons are able to behave like small magnets. If no magnetic field is applied to a complex that contains free electrons, the spins are pointed in random directions. But if a magnetic field is applied to a complex that contains free electrons, then the free electron behaves like a bar magnet. It takes one of two orientations. In the lower energy orientation, the electron is parallel to the magnetic field. In the higher energy orientation, the electron is anti-parallel to the magnetic field. So the values of the two energy levels are equal to these two equations that I have displayed here, where mu sub B is the Bohr magneton, G is the G factor, and B is the magnetic field. Now, the separation between these two energies is called the Riemann splitting. So we can use this equation that I have below to obtain the difference in energies. Next, if radiation of a specific frequency is applied in the presence of a magnetic field, then a transition from the parallel to anti-parallel state can occur. And this transition happens if the population of electrons in the lower energy state is greater than that of the higher energy state. So what affects this energy of the transition? Well, one thing is the G factor, or the spectroscopic splitting factor, and that is a term that offers details about the electron spin momentum. It changes depending upon the electronegativity of the atoms that are coordinated to a metal. So the G factor is made up of two terms and is formed by the equation here on the right. G sub L represents the spin orbit coupling effect. G sub E represents a G factor value for a free electron. And the G sub L term is a dot product of the frequency and radius from the metal nucleus to a free electron. So a more electronegative atom will pull the electron towards itself, increasing the radius between the copper nucleus and the free electron and increasing the G factor term. So this G factor is involved in the total energy levels for the two-spin system, which is defined as the following equation that I have displayed. So this equation involves the electron Zeeman splitting, the nuclear Zeeman splitting, and the product of the two. So the product contains a new term, which is assigned as A, and this term is the hyperfine coupling constant. So the hyperfine coupling constant represents the amount of time that an electron is spent in proximity to the metal nucleus. Similarly to the G factor, this term changes depending upon the electronegativity of atoms that are coordinated to a metal. So the higher electronegativity of a ligand, the increased attraction that the electron will have to that ligand, and the less time that the electron will be spent in proximity to the metal nucleus. So in that case, A will decrease. Overall, the two terms, G factor and hyperfine, are inversely related. They explain the same concept, just in different ways. Now, using this theoretical information, we had hypothesized that because complex 2 contains two oxygen atoms, this complex's ligands will have a greater electronegativity than the other metal ion complexes, and therefore will receive the smallest hyperfine and the largest G factor. Now, between complex 3 as well as complex 1, the differing hybridization will actually impact the differences between the G factors and the hyperfines. In complex 3, every ligand we see, or every nitrogen atom, is sp2 hybridized. For the sp2 hybridization, the orbitals are more S-like in character. So the nitrogen atom is closer to the copper due to the S character being spherical and stout. And because the nitrogen atom is closer, there's more attraction between the free electron and the nitrogen. So the radius between the metal nucleus and the free electron then becomes larger, so the G factor will become larger. Overall, by this logic, complex 3 is predicted to have a larger G factor and a smaller hyperfine than complex 1. One last thing to mention before we analyze the ESR spectra is that we are taking one for DPPH in order to measure its G factor. So DPPH represents an electron that is free from orbital momentum coupling. Thus, we can reference its G factor as a standard to set up the parameters of our experiment. So we had hypothesized that since DPPH is free from the spin-orbit coupling because of its delocalized free electron, it will have a G factor value that is less than the 3 coordinated compounds under analysis. This is because for DPPH, the G sub L term goes to 0 since there are no nuclear electron interactions. Next, this experiment has 2 parts. So first, the 3 copper compounds would be synthesized and prepared in the respective ESR tubes, and then a magnetic field would be scanned at a set frequency. And then finally, each of these ESR tubes would be placed in the cavity of the spectrometer, and then a spectrum would be captured for each sample. Now, we did not have access to the ESR instrument, so during our lab time, we synthesized complex 2 and then captured a UV-Vis spectrum for that, and then got data from our TAs. So after we received the data from our TAs, we examined DPPH, and we see that it only contains one major peak. So we use its maximum and minimum peaks to find its experimental center field value that would be right in the middle of that. And then we determined that its experimental G factor is equal to 2.0043. But wait, what about its hyperfine coupling constant? Well, we can't determine it experimentally. For DPPH, because the free electron is delocalized across the whole molecule, there is relatively an equal probability of the electron to be in any d orbital. Therefore, we're unable to determine this coupling constant because there is not a high enough resolution or strong enough magnetic field to resolve each of these individual probabilities of the electron being in a specific orbital or a different orbital. So in theory, you can calculate each individual probability. However, experimentally, we are unable to do this. So similarly to the analysis of DPPH, for the 3 copper complexes, we determine the center field value by taking the average of peaks 2 and 3. We're unable to use peak 4 due to polarization-dependent signals. So after we determined the center field value, we got the specific G factor for each individual complex, as well as the specific average hyperfine for each individual complex. And please note that in each individual spectrum, we will see 4 peaks for copper due to its ±3/2 nuclear spin, along with its ±1/2, which will split the energies even more. Now here are our spectra for complex 1, complex 2, and complex 3. And because we were able to obtain the spectra, we are able to obtain all G factors and hyperfines to then evaluate our hypotheses. So based on the resulting data here, it is clear that our hypotheses have been confirmed and prove the theoretical trends that we had discussed. So complex 2 has the smallest hyperfine coupling constant and the largest G factor because of its more electronegative ligands. And complex 3 seems to have a smaller hyperfine coupling constant and a larger G factor than that of complex 1 because it has ligands with less hybridization. And lastly, DPPH has the smallest measured G factor. Now, 2 discussion points to go over before we close. Going back to energy, the total transition energy levels for the 2-spin system is defined by the following equation here. So the Zeeman splitting of the electron spin energy levels is significantly larger than that of the nuclear spin levels. And we can see that in this figure here. This is because the mass of a proton is so much larger than the mass of an electron. Thus, the mu sub n term or nuclear magneton term for the proton is extremely small compared to that of the electron. Therefore, since the nuclear Zeeman term becomes very small, it may be negligible and will not have a great effect on the total transition energy equation in comparison to the larger electron Zeeman and hyperfine terms. And finally, using the absorption peak magnetic field, we can determine that the difference between the lower and higher energy states, or delta E, of DPPH is equal to this first value right here. So then using that value and the Boltzmann ratio, the population ratio between the 2 spin sublevels of the molecule at room temperature is equal to 0.00157. So it makes sense that this number is small or less than a value of 1, because in order for an ESR spectrum to develop, a signal is needed that will come from the excitement of an electron from the lower to higher energy state. Now, if the 2 states are equally populated, no electrons can be excited, and then no signal will be produced. therefore no spectrum can be obtained. So it's clear here that the population difference between the two sublevels is heavily dependent on temperature. So the temperature needs to be small in magnitude to ensure that the electrons are not excited before the collection of the spectrum, and that the majority of the electrons remain in the lower energy state. Now, overall, this investigation contains 3 copper complexes that simulate molecular environments within proteins and corresponds to amino acids within these proteins. So the trends regarding the G factors and hyperfines can be then applied to larger biological compounds. For instance, if we have a protein that we know binds to copper, we are able to calculate a G and A value for the compound by using its spectrum. And if these terms are similar to one of the model compounds that we had studied, so for example, if its G factor and hyperfine are similar to complex 2, then we can infer that copper is sitting in a space that contains those specific amino acids and oxygen atoms. So this is a method that may be used to determine exactly where in a protein the copper may be sitting. And of course, more applications include food sciences, medicine, and much more. Lastly, I just want to give a huge thank you to our TAs, Sydney and Tyler, for all their help and support in the lab, as well as Aya for being such a great lab partner. And I want to, of course, acknowledge Dr. Wagner, the University of Pittsburgh, as well as my peers. Thank you so much for watching.